Hello everyone, I am Mastan. In this video, I am going to show how to read an analog signal using the F28379D LaunchPad and the C2000 Microcontroller Blockset in MATLAB Simulink. Before going into the Simulink model, let us first identify the main header connectors on the LaunchPad. The board has several connectors, but in this video, we mainly focus on the header connectors marked as J1 to J8. These connectors are used to interface PWM signals, GPIO pins, and ADC inputs. Now, I will highlight each connector one by one. This is J1, this is J2, this is J3, and this is J4. Similarly, these are J5, J6, J7, and J8. Now this is the back view of the F28379D LaunchPad. Similar to the front side, here also we can identify the header connectors J1, J2, J3, J4, J5, J6, J7, and J8. To see the pin names properly, I am going to zoom in on these highlighted portions. In this zoomed view, we can observe that the ADC channel names are printed near J3 and J7. These names are very important because the same ADC channel names must be selected later while configuring the ADC block in the C2000 Microcontroller Blockset. Near J3, we can see ADC channels such as A14, AC3, AB3, AA3, AC2, AB2, and AA2. Similarly, near J7, we can see another set of ADC channels such as A15, AC5, AB5, AA5, AC4, AB4, and AA4. So while doing the hardware connection, we should note the exact ADC pin used on the LaunchPad. The same channel name must be selected in Simulink. Otherwise, the ADC block will read a different input. Now, after identifying the ADC pin names on the LaunchPad, let us see how to select the ADC block in MATLAB Simulink. First, I will open the library browser in Simulink. Here, we can see different toolboxes and block sets. Since we are working with the F28379D LaunchPad, I will open the C2000 Microcontroller Blockset. Inside this blockset, different C2000 device families are available. For the F28379D LaunchPad, we need to select the F2837XD family. After opening F2837XD, we can see different blocks, such as ADC, GPIO, PWM, DAC, ECAP, EQEP, SPI, SCI, and other peripheral blocks. To read any analog input signal through the LaunchPad, we need the ADC block. Therefore, I will drag the ADC block into the Simulink model. This ADC block will be used to read the selected ADC channel, which we will configure according to the ADC pin name available on the LaunchPad. Before selecting any ADC channel in Simulink, we need to understand how the ADC pin names are written on the LaunchPad. In these names, the first letter A indicates that these pins are related to the ADC input section of the controller. After that, the middle letter represents the ADC module that should be selected in Simulink. The last number indicates the ADC input channel number. Therefore, every ADC pin name gives us two important details, the ADC module and the input channel number. These two details are used for configuring the ADC block in the C2000 Microcontroller Blockset. Now let us take AB5 as an example and configure the ADC block for this pin. From the LaunchPad pin name AB5, the middle letter B represents the ADC module. So in the Simulink ADC block, I will select ADC module B. The last number is 5, which represents the ADC input channel number. So in the input channel selection, I will select channel 5. Now the AB5 pin on the LaunchPad is linked with this ADC block in Simulink, and this block will read the analog voltage applied at this pin. This is the J7 connector from the front view, and this is the same J7 connector from the back view. Here, pin number 65 on the front side is the same as AB5 on the back side. So when analog voltage is applied to this pin with respect to ground, it will be read by the ADC block configured for AB5. Before applying analog voltage to 65th pin, let us first understand the basic ADC fundamentals required for safe operation. The first important point is the ADC input voltage range. The voltage applied to the ADC pin must always be within the allowed ADC input range of the controller. If we apply a voltage higher than the allowed limit, the ADC pin or the controller may get damaged. The second important point is the ground reference. The external analog signal must be applied with respect to the launchpad ground. Without a common ground reference, the ADC reading may be incorrect. The third point is ADC count. The ADC does not directly give voltage. It gives a digital count. Later, we convert this ADC count back into voltage using the ADC reference voltage and ADC resolution. So, before connecting any sensor or external signal to the ADC pin, we must check three things: the input voltage range, the ground connection, and the ADC count. Now let us understand the relation between input voltage and ADC count. For the F28379D LaunchPad, the ADC input voltage range is 0 to 3 volts. That means the analog voltage applied to the ADC pin must remain within this range. Next, the ADC converts this analog voltage into a digital count. Since the F28379D LaunchPad uses a 12-bit ADC, the output count ranges from 0 to 2 power 12 minus 1, that is 0 to 4095. In general, for an n-bit ADC, the maximum ADC count is given by 2 power n minus 1. So for a 12-bit ADC, the maximum count becomes 2 power 12 minus 1, which is 4095. Similar to the F28379D LaunchPad, other controllers also have their own ADC input voltage range and ADC count range. For example, in ESP32, the ADC input voltage range is generally considered as 0 to 3 volts, and since it uses a 12-bit ADC, the output count range is 0 to 4095. Similarly, for Arduino DUE, the ADC input voltage range is 0 to 3 volts, and the ADC output count range is also 0 to 4095 because it uses a 12-bit ADC. But in Arduino Uno, the ADC input voltage range is 0 to 5 volts, and it uses a 10-bit ADC, so the ADC output count range is 0 to 1023. This is because for a 10-bit ADC, the maximum count is 2 power 10 minus 1, which is 1023. From this comparison, one thing is clear. Before applying any analog voltage, we must check the ADC voltage limit of that controller. After that, based on the ADC resolution or simply the ADC bit number, we can know whether the output count will be 0 to 1023 or 0 to 4095. Now this graph shows how the ADC count changes with input voltage for a 12-bit ADC with a 3-volt reference. When the input voltage is 0 volts, the ADC count will be nearly 0. When the input voltage is 1.5 volts, which is half of the input range, the ADC count will be nearly 2048. When the input voltage reaches 3 volts, the ADC count will be nearly 4095. So, any input voltage between 0 and 3 volts will give a corresponding digital count between 0 and 4095. This relation is linear, so as the input voltage increases, the ADC count also increases. Now we have understood the relation between input voltage and ADC count. Let us verify the same concept practically using the F28379D LaunchPad. For this practical test, I am using the signal generator option available in the DSO. I will connect this signal generator output to 65th pin of the LaunchPad. Here you can see the physical connection. The signal generator output is connected to 65th pin of the LaunchPad. The ground terminal of the signal generator is connected to the ground pin of the LaunchPad. This common ground connection is important for getting the correct ADC reading. Now let us move to the Simulink model. Here the ADC block is already configured for AB5, which means ADC module B and channel 5. To read the ADC count in real time, I will run the model using the monitor and tune option. The ADC output will be observed using this scope in real time. First, I will set the signal generator output to 0 volts. Since the input voltage is 0, the ADC count should be close to 0. Here we can observe the ADC output in the scope. Now I will increase the signal generator output to 1 volt. Since 1 volt is 1/3 of 3 volts, the ADC count should be nearly 1/3 of 4095. So the expected ADC count is around 1365. Here we can observe the corresponding ADC count in the scope. Next, I will test the mid-scale point by applying 1.5 volts. This is the middle point of the 0 to 3 volt ADC range. So the ADC count should be around half of 4095, which is nearly 2048. Here, the scope output shows the corresponding mid-scale ADC count. Now I will apply 2.5 volts to the ADC input. The expected ADC count is 3413. In the scope, we can observe that the ADC count is close to 3413. Now I will rotate the knob and change the input voltage continuously. You can see that when the voltage is reduced, the ADC count is also reducing in the scope. Similarly, when I increase the voltage, the ADC count is also increasing. This confirms that the ADC count follows the input voltage in real time. Until now, we have seen the ADC output as a digital count, but for control algorithms or sensor-based calculations, this count cannot be used directly. First, we need to convert it into the actual analog voltage applied to the ADC pin. So now let us see how to convert ADC count into input voltage. To convert ADC count into input voltage, we use this relation. Here for the F28379D LaunchPad, the reference voltage is 3 volts and the maximum ADC count is 4095. So the scaling factor for converting ADC count into voltage is 3 divided by 4095. For Arduino Uno, the reference voltage is 5 volts and the maximum ADC count is 1023. So the scaling factor is 5 divided by 1023. Now I am moving back to the Simulink model. Here, the ADC block gives the output as a digital count. To convert this ADC count into voltage, I am adding one gain block after the ADC block. For the F28379D LaunchPad, the scaling factor is 3 divided by 4095. So I will set the gain value as 3 divided by 4095. Now, the output of this gain block gives the actual input voltage applied to the ADC pin, and we can observe this voltage in the scope. Now, after adding the gain block, the scope is showing the voltage value instead of ADC count. Let me check it with a few input voltage levels. Here, I am setting the input to 0 volts and the scope is also showing nearly 0 volts. Now, I am changing it to 1.5 volts. You can see that the scope value is also close to 1.5 volts. Next, I am increasing it to 2.5 volts and again, the scope value is close to 2.5 volts. This confirms that the 3 divided by 4095 scaling factor is converting the ADC count back into voltage correctly. Now, instead of testing fixed voltage values, I will rotate the knob and vary the input voltage continuously. Here, the scope is showing the converted voltage value. When I reduce the voltage, you can see the scope value also coming down. Now, when I increase the voltage, the scope value is also increasing. This shows that the voltage conversion is happening in real time. Until now, we tested the ADC concept using the F28379D LaunchPad and Simulink. Now, let us check the same voltage measurement concept using a simple Arduino Uno board. The controller is different, but the basic idea is the same. Read the analog voltage, get the ADC count, and convert that count back into voltage using the proper scaling factor. Here I am connecting the signal generator output to the A0 analog input pin of the Arduino Uno. The signal generator ground is connected to the ground pin of the Arduino board. Since Arduino Uno works with a 0 to 5 volt ADC range, I will keep the applied voltage within this limit. Now let us move to the Arduino IDE. Since the input signal is connected to A0, we have to select analog pin A0 as the input pin. In the code, A0 is assigned to the variable analog pin. Then inside the loop, I am using analog red to read the signal applied at A0. This function reads the analog input and returns the corresponding ADC count for the voltage applied at the A0 pin. Next, I am converting this ADC count into voltage. For that, I am multiplying the ADC value with 5 divided by 1023. Here, 5 represents the maximum input voltage of the Arduino Uno ADC. And 1023 represents the maximum ADC count for the 10-bit ADC. After this calculation, the variable voltage gives the actual input voltage applied at A0. So instead of plotting the ADC count from 0 to 1023, we can now plot the voltage from 0 to 5 volts. Now I will open the serial monitor. When I apply 1 volt from the DSO signal generator, we can observe nearly 1 volt in the serial monitor. Similarly, when I apply 2 volts, the serial monitor also shows nearly 2 volts. This confirms that the voltage applied at A0 is being read and displayed correctly. Now I will rotate the signal generator knob and vary the input voltage continuously. You can see that when I reduce the voltage, the value in the serial monitor is also reducing. Now when I increase the voltage, the displayed value is also increasing. This shows that the ADC voltage conversion concept is working properly on the Arduino Uno also. In this video, we understood how an ADC reads analog voltage and converts it into a digital count. We verified this practically using the F28379D LaunchPad and also repeated the same voltage measurement concept using Arduino Uno. The important point is this: before connecting any analog sensor, we must know the ADC voltage range and the correct scaling factor. I hope you gained some useful knowledge by watching this video. In the next video, I will connect the ACS723 current sensor and use this same concept to measure current,